Now, for this problem, we're going to relate Kc, the equilibrium constant, to a, reaction for which we will calculate the cell potential. Here, so ln of K, in this case Kc, equals minus n. Hold on, something's not right here. There we go. Equals, and I can go to my conversion and equation sheet, minus RT over NF ln K. There you go. So here's the equation we're going to use, and we're going to have to actually find the cell potential and find all of these variables where N and F. N is the number of electrons in the redox reaction. F is the Faraday constant. R is 8.314 joules per mole Kelvin. T is temperature in Kelvin. And at some point, we will solve for Kc, the equilibrium constant. But we will figure out the cell potential first. Is this the same? No, it's not the same cell potential as the last one. Our process is always to go look at our standard reduction potential table, find our magnesium, find our iron 2+, and write down their half reactions. Where can we find these tables? Well, good question, Tamiwa. So first off, you can find them in the homework problems themselves. So they're in there. And then the second place is I need to post a copy of this so you can print it out easily. That's what I did. I actually just copied and pasted it from one of the homework problems. Again, remember we flipped the reactants and products because that's how you get an oxidation half reaction, and we changed the sign of the potential from minus 2.37 on our SRP table to plus 2.37. Let me go to my table again. This one is minus 0.45. It would be great if we had one that was just plain positive, but we haven't been given that here. Straight add them up. Yes, thank you, Tamiwa. I need to get those all printed up for you and in. So let me make a note of that while I'm here. So I'll send out an announcement when that comes out. But for now, 2.37 minus 0.45, 1.92 volts. Now I know my N, which is my 2 electrons, my F, my R, and my T. Let me rearrange this. So now I'm going to bring my N and F up to the top. And let me find this part here, and then I'll do the exponential to get rid of this natural logarithm. Minus 2 times 96,485 coulombs per mole of electrons, 1.92 volts. And my temperature, 25, is going to be 298 Kelvin. Let me multiply this out. 2 times 96,485 times 2.09 divided by 8.314 divided by 298. I get 162.78, 163 minus 163 because I got to have that minus there. Yes. Hold on. My apologies. I should look at my own conversion and equation sheet. This should be, there is no minus sign in this. And let me pull up my conversion and equation sheet. To make sure I've got this right. Yeah, there's no minus sign in there. And I'll show you how I know that in a second here. But now, if you want to solve for Kc, you have to take the exponential of both sides. And so Kc will be e to the 163rd, which is going to be a large number, and that's why you're going to enter the answer in scientific notation. 6.17 times 10 to the 70th. Which is a very large number indeed for your Kc value. This is very product favored. At equilibrium, there are essentially no reactants left. And I'm sorry I messed up that. Let me put my plus sign in here now. Sorry, I got confused with the delta G equation for that. So, and what we will see is that, so while E naught cell is positive for a spontaneous product favored reaction, Kc is very large and positive exponent for a very product favored reaction, and delta G is large and negative for a product favored reaction that is spontaneous. That's what I have for that one.